Yeah, thank you. Thank you. Yeah, so welcome to this second session. I always tell my students and collaborators that there are only two things that really should attract us. Either it should be intellectually fascinating or it should be potentially useful. And what I'm going to present you here has both. It is intellectually fascinating, and I'll show you it is potentially useful. So let's immediately move on. What is cryptography? So of course, the art of secrecy, and cryptography covers many, many aspects, but let's concentrate on the simplest one, the easiest also to understand. Just you want to send a message between A and B, and let's say Alice and Bob, and you don't want that any other person, like the adversary Eve, can intercept that message. That's a very, very old problem, and it's still extremely timely today. And essentially, there are two ways of achieving such a goal. One is based on complexity theory, where the key is public, so it's often called a public key cryptography. And this public key, actually contains the decoding key. However, to get this decoding key out of this public key is difficult. Come back to that. On the other side, here on the right-hand side, there is another class of cryptology where the secrecy is based on information theory. Here you have a key that needs to be secret, so that's not so easy. However, the good thing here is that the security of this type of cryptography is proven. It's really a kind of consequence of Shannon's information theory theorems. So that looks very good. Now, on the left side, the difficulty here is really to understand what it means to be difficult. And it really means that people have tried, including very brilliant mathematicians, and even these very brilliant mathematicians have failed. So if the best guys in the class have failed, the problem must be difficult. But difficult doesn't mean impossible. And there is indeed, both on the algorithmic side and on the hardware side, progress. And so things that are difficult today may become easy tomorrow. And that is the big thread, how to solve that. Now, on the right-hand side, of course, the difficulty is to have all these keys that need to be distributed between all possible pairs of partners. So how do you do all that? So once you have your message that Alice wants to transmit in a confidential way to Bob, she uses a key. And then they combine these two, and then they use what is called symmetric cryptography, something that is very fast. You can really do it at 100 gigabytes per second and so on. But the problem then is this, how do you distributing these keys, these secret keys? So of course you could have a trusted courier, but you see that this is not very practical. Even with this VTOL, it's probably still not going to be that practical. Public key, that's good, it's pretty good, but it's not going to resist the quantum computer that is coming. I'll say a few words about that. So then a possible solution, and that's the one I will present mostly, is quantum key distribution. So why is that so important now? So for instance, here you have a picture of a center owned by the NSA, but you would have similar pictures in China, Russia, and probably many other countries that can essentially store all the communications that goes on over the entire world. Essentially, everything gets stored there. And probably some private company do the same, and so on. And so the idea is not that they can immediately decipher everything, but they can store everything, so they can store the encoded text, the ciphertext now, and just wait. Wait until you have mathematical progress or hardware progress, maybe in 10 years, 20 years. Most of course, of the secrecy of today in 20 years have lost all their values. But depending some kind of information, you want it to remain confidential over maybe a lifetime, a century. And then you have a problem with this. There's no way to fight against these store now, decrypt later attacks. And what I guess is that already today, for instance, the NSA can decipher what they want, but they cannot decipher everything because it takes still time. But I guess they can decipher a few hundred messages per day. Here you have the very well-known Morse law. Let's look at it more on the size of the transistors. And this size is now really entering the quantum regime. There's nothing against that. This is going to happen. This is actually happening now. And that essentially, it's well summarized probably with this sentence, due to Michael Berry. The theory of electromagnetism was developed in the 19th century and has been the basis of all information technology in the 20th century. And likewise, quantum theory was developed in the 20th century and will be the basis of the 21st century. So a lot of the technology of this century that we are entering now will be based on quantum. And so then there is the problem concerning this store now, decipher later. Later, in some times, come back to that, there will be a quantum computer. And it is already known that a quantum computer will break today's crypto systems, these public key systems that are used today. So the question is, how soon should we actually worry? Can we just wait? And probably you already know the answer. We cannot just wait, because it's going to depend, how long we can wait is going to depend on for how long do we want our encryption to remain secure. Again, if it's 1 year, don't worry. If it's 20 years, it's already too late. How long is it going to take to change the infrastructure? It's going to take 5 to 10 years. And how long is it going to take for a large-scale quantum computer to be built? Let's say Z year, something like 20 years. And then there is a very elementary theorem. If x plus y is larger than z, then panic. And we are in panic mode. It is essentially impossible today to guarantee confidentiality over 20 years. Now, how long will it take for this quantum computer? There's also a talk after the coffee break on that. But so one of the leading specialists, Michele Mosca, he says, okay, there is one chance in 7 that we have one in 26, one in 2 in 31. So it's coming. And this is also acknowledged by the European, so ETSI, European Telecommunication Standard Industry, by the NSA. Everybody agrees. So there's no doubt that this is coming, and there is a problem here. So how can we solve that? There are 2 ways, essentially, to transit to quantum-safe cryptography. One way is to say, okay, we still continue with complexity-based cryptography, but instead of using factoring, probably all heard that factoring is at the basis of what we use today with the RSA protocol, we go to another problem, which is deemed even harder than factoring, more difficult. Mathematicians have even less idea how to solve that kind of problem, and apparently the quantum computer might not be able to solve that one. So that's a possibility. The other one is to move to physics-based. And I'm a physicist, so obviously you know on which side I am. Quantum key distribution. Now, what is the advantage of the post-quantum crypto algorithms? Essentially, there's not much change. You change one algorithm for another one. Okay, in practice, it's a bit more complicated because problem being more complicated, you need longer keys. I mean, there's a big change in the infrastructure, but the spirit is the same. However, the negative point here that we are again making just a wild bet on the unknown. You know, when RSA came out, it was promised that this would last for the age of the universe. And it lasted about 30 years. So it's just not possible to foresee progress in algorithmic and in hardware, in physics. So that's certainly good for a while, but not on a long time scale. And this is really, again, the very important point. This idea that you can store now and decipher later will again be a possible attack here. You can just store everything and wait 20, 30 years, and then you can decipher. And for some information, at least, this is too short. Think of the information about the health of your kids. these you want to remain confidential for their entire lifetime. On that side, on the physics-based, this is provenly secure, so it's a mathematical proof. It is backward resistant, so you can no longer store now and decipher later. However, for the time being, it is much more expensive. That will also change in the future depending on developments. And it is a big change. I think this is really the major drawback here. It is a big change in infrastructure and mentality. You have to change the knowledge of the security experts. Now, it is likely that both will find some applications in different market sizes. So here, maybe just for those who really know. So RSA is that what is used today, or elliptic curves. This we know will no longer be valid. The symmetric encryption like AES, that is believed to remain highly confident, highly secure, because there is essentially very little structure in it. And if there is no structure, there is no handle to attack it. And then there are all these different systems that are presently under investigation. So let me come now to the more physics part, quantum communication. So you may now define it in kind of abstract way as the art of transferring a quantum state from one location, Alice, to a distant Bob. So we have Alice and Bob, we have a quantum state on one side, and at the end of the protocol, you will have that quantum state on the other side. Of course, that is fascinating, to me at least. And what is it good for? What is potentially useful? Well, there are two kinds of answers. One is kind of fundamental answer. You know, at the end of the day, information is always carried by the state of some physical system, and physics, to the best of our knowledge today, is quantum. So this is really the limit. That's the intellectual fascination. Now, the potential usefulness comes from the fact that a quantum state cannot be copied. This comes under the no cloning theorem or things like that, which I'm not going to prove here. And that looks like a very negative statement. But let's first look, why are physicists totally convinced about this no cloning theorem? Well, the fact is that if one could copy a quantum state, that would both violate the Heisenberg uncertainty relation, so the very fundamental of quantum physics, and it would also violate the impossibility of fast-than light signaling. And it would also violate the fundamental of relativity. So the possibility of violating this no cloning theorem would really violate everything we know in physics, and so it's probably one of the best known facts we have in physics. Now, why is it useful? This looks negative because one cannot do something. That's not positive. Yes, except that now it's the adversary that cannot do something. One cannot intercept a message and copy it, as we do, or as people do regularly on the classical communication. So here, the store now, decipher later attack has become impossible. So this major attack is impossible thanks to this impossibility of cloning quantum states. So how do you do quantum communication? Well, you start with a photon, you send it, for instance, to a beam splitter, sometimes a nonlinear crystal, you split it in two, the photon explores two paths, hits two detectors, but only one detector detects the photon. That's really basic of quantum physics. And so because only one of the two detectors detects the photon, this is really quantum randomness. You get a random answer. There's no way to control which detector detects the photon. It is intrinsically random. And because the same photon can explore more than one path, this is the basis of quantum non-locality, or in more technical words, is entanglement. Now, just the randomness here, that is the basis then of quantum random number generator. We'll see more about that. And the kind of non-local randomness, that's the basis of quantum key distribution. So let's look first at this quantum key distribution. So just trying to Here to take out part of the signal will not be useful because you have a single photon. And if the adversary Eve gets that photon, Bob does not get it, and vice versa. If Bob gets it, Eve doesn't get it. So Eve, in this simple attack, does not get any information about Bob's data. She gets some information, but not the ones that will be used at the end, so it's not useful for them. Remember, this is not sending a message, this is sending a cryptographic key, and the key at the end of the day will be made out of those photons that Bob received. You could also do an intercept resend, but because of this no cloning, this is again not going to be useful. Then at the end of the day, you have to study all possible attacks, so this becomes really theoretical physics. And what is interesting is that one can really prove that given the bit error rates, and we call it the quantum bit error rate, so the error rate in this quantum communication channel, that is really bounding the Shannon information accessible to Eve. This is really the mathematical part of that. And then we can, once we know or we have a bound on Eve's possible information, we know how much privacy amplification we need to apply in order to make sure that Eve's information gets exponentially smaller. Okay, and now we founded already quite some years ago this company, IDQ, ID Quantique. And okay, first we had a university demonstration between Geneva and Lausanne, but now there are actually banks in Geneva that have their backup systems in Lausanne. There is a law in Switzerland that the backup system, the recovery center, has to be at least 50 kilometers away. Here it is about 70 kilometers away. And this is actually how Alice looks, and Bob looks the same. And then you have the encryptors and decryptors, and this is really used continuously day after day by some customers today. So this is how it was, Alice was looking at that time. Okay, now today Alice and Bob look a bit slimmer, but it's the same idea. Let's maybe look at what is inside Alice and Bob. So inside Alice and Bob, first of all, you have a lot of electronics for this, where is it written? Privacy is, yeah, here, privacy, amplification, as I mentioned, error correction, synchronization. You need all that. So you have that. You also need some randomness, and of course we use quantum random number generator. But then you have also some optics, a laser, intensity modulator, attenuator, couplers, things like that, pin, so standard detector. On the other side, again, isolators, very standard components. Even these Faraday mirrors are standard telecom components. What is not standard are the single photons detectors here. So actually in these boxes, Alice and Bob boxes for this quantum key distribution, you use very, very standard technology except for the detectors. The detectors need indeed to have the sensitivity to go down into the quantum regime, into the single photon regime. You cannot have a standard detector there. But the rest is very standard. And so you see from that kind of picture that there is no reason intrinsically for these kind of boxes to be more expensive than telecom boxes. Except for the detectors, it's all the same. And detectors make a lot of progress. So here you have some demonstrations, okay, 300 kilometers. You see also that the bit rate is very slow, but there is certainly lots of room of progress, and I think very soon we'll have gigabits per second of provably secure key, which again is just providing the keys. When your encryptors can run 100 times or 1,000 times faster, that's not a problem. It just means that you can change the key every fraction of a second. Now there's another question here is, what about certification? There is no certification today, this is too new. And so the way this company went around that is, in addition to do the quantum key distribution, they do the standard public key distribution system. This part has been homologated, certified, and standardized. This part has this no cloning, so impossibility of store now, decipher later feature. And then you just combine the two keys, and in this way you get the certification and the security. Let me now come to randomness, the quantum random number generator. The first message here, and I guess that's pretty well known, is that there is no way to have security without good randomness. okay, we all have plenty of passwords. We probably have no way to remember them, so we use the same all the time, or we use, non-random passwords. And for our daily life, it's probably good enough. But if you think now of more demanding applications, you need randomness. There's no way around that. And Snowden has told us that one should not trust pseudo-random number generator. You know, even those that are certified by NIST have been proven now to be fake or have built-in weaknesses. So you need to go for physical random number generators. But in physics, there is only quantum physics that provides randomness. So you need to go to quantum random number generator. How does it look? Well, the principle is extremely simple. You just have a source of photons, a beam splitter, two detectors, single photon detectors, but these ones do not need to be at telecom wavelengths, so they are much cheaper. And one detector you call 0, the other one you call 1, and then you get your string of random bits. It's very simple. And the fact that it is simple is useful because you know exactly where the randomness is coming from. It is not just complexity where you don't really understand what is going on. Okay, and it's practical. Let's look. So you actually, all that is in this little cubic centimeter cube. Then a bit of electronics, and now in this device, about 4 centimeter large, you get 4 megabits per second of balanced random bits out. And so we have already produced, I don't know how many thousands of these. Here you have certification. Okay, in German it would be the BSI, in French it's l'Agence nationale de la sécurité des systèmes d'informatique. So okay, here the certification exists, and this is the kind of solution that some companies now develop. So this was Keymile in this country, by the way. So you have a standard electronic board where you recognize some FPGAs, interconnections, and all the kind of normal stuff. But if you zoom on the right spot, here you have actually this little cube. So this is actually a quantum random number generator. So today you can already have just standard electronic boards where one component is a quantum one. And that one provides the randomness, the entropy that is needed for this security. So this is an encryption card by this company. Okay, we made progress on that. What is now coming, the next step, will to make that quantum random number generator even much smaller. And this is done now in collaboration, it's actually not written here, with some South Korean company, SK Telecom. And it should really become small enough that you can have it in every iPhone or smartphone. Maybe Samsung will be first because we are collaborating with Korean companies. And of course in every servers and so on and so on. So there's absolutely no reason to doubt that you will have quantum devices in your pocket in a few years, without noticing it probably. The company profile just very quickly, so it's already pretty old. We had a slow start, but now the growth rate is nice. We have offices, okay, the main in Geneva, so in South Korea, in China, in Bristol, more is to come. About 100 employees worldwide. Let's come back to physics. So to do this quantum key distribution, you send photons, individual photons, via an optical fiber. The optical fiber is the standard telecom optical fibers that we are all using, that is installed all over the world. But these fibers, they are kind of extraordinarily transparent, but they're not perfectly transparent. So they're a bit of loss, about 0.2 dB per kilometer. And that means that after some distances, your single photon gets so attenuated, so the probability that it makes it to them, that essentially you get nothing out. For instance, if you have a perfect noise-free detector, so perfect, 100% efficient, you have an ideal source of 10 gigahertz of single photons. It would still take centuries just to get one photon over 1,000 kilometers. So that's completely ridiculous, of course. So after, let's say, 400, maybe 500 kilometers, it just stopped to work. And this is probably one of the main limitations of today's quantum key distribution. So how can you go around that? Again, now I'm going to the intellectual fascination. Let's suppose you have Alice here and a kind of intermediate Bob, and you have entangled these two. You have these quantum correlations between these two. Now, in the middle, we have a second photon or a second quantum system entangled yet with Bob, the ultimate, I'll call it Charlie now, the one on the right-hand side. Now, there is something you can do according to quantum physics. It's teleportation. It's even more cool than the planes we saw before, but probably not as practical for humans. So you do a teleportation. You teleport the state of this photon onto that one. And now you have entanglement over twice the distance. So this is really on the paper the way to extend the distances. And it's really fascinating because now you have entanglement between photons that never interacted. Now this, I admit, especially in such a presentation where I cannot go into any details, may look just like magic, and it is kind of magical. However, it is very well understood and mastered physics. So this is things that people do really in the lab and outside the lab. The Chinese have recently shown teleportation between a low-orbit satellite and ground. So it was really 500 kilometers about. So you can do all that, and with that you can then really build a quantum repeater. Now, however, when you have a network, and then you see we have networks with that, one requirement that comes when you have a network is synchronization. And synchronization means you need a memory. You have to say to one photon, wait a while. Photons don't easily wait. So what you need is a quantum memory. Okay, so that's just a distribution of entanglement. Now, a quantum memory. So there are different ways of doing it. In Geneva, we are working on crystals, optical crystals, or transparent crystals, which are doped by billions of ions, rare earth ions, typically europium, let's say. And we send a photon in, and the photon gets absorbed. That's not very difficult. I can also absorb a photon with my hand. However, here we want to do it in a reversible way, in such a way that photon come out now, and the photon comes out, keeping all the properties, all the quantum properties, entanglement and all that. And in this way, you can then synchronize your quantum network. So this is under development, and okay, today we have an efficiency, okay, depends, many numbers, but okay, that was already 10 years ago, I see 20%, so we are a bit better. Here you see these optical crystals and so on, can have nice pictures. This one is more the europium and the yellow light, since it absorbs at 583 nanometers. And you can indeed show that you still have violations of Bell inequality, so you do indeed maintain entanglement and can go to longer distances. All that is very nice. However, this is still, first, if you want to see more, you have a review paper in this Physics Today, so a semi-popular review paper here. Here you have storage times that, let's say, to 1 millisecond. But okay, to be really useful, we should extend that scale by at least 1 or 2 orders of magnitude, and the vertical scale by 1 order of magnitude. And admittedly, the quantum repeater today is in that stage. So it's not ready to be put in a box and shipped around. It's not yet commercial at all. But again, there's a lot of fascinating physics here in. So what do we do today to go around these distance limitations of, let's say, 400 kilometers? Well, today, the only way to do that is to have a quantum link and then go from quantum to classical and back to quantum. So, of course, here you have to trust this node. That's why this is called trusted node. So typically in Geneva, between the university, okay, some technical school and CERN, so we had a little triangle. That was also already years ago. Years doesn't show here. The Chinese make it, of course, on a very different scale. So they have these trusted node networks between Shanghai and Beijing. That's 2,000 kilometers with 30 trusted nodes in probably governmental centers. So this is the only way practical today to beat this 400 kilometer limit. Okay, so now in a more complete scenario, you could imagine that you have a kind of backbone where you really use quantum key distribution. But then to access this backbone, you may use all kinds of ways, typically using these post-quantum cryptography access possibilities. That will really depend on every client. So for some of them, these post-quantum crypto systems will be good enough because we don't need 50 years of security. So some of us, we will need QKD access because we really want this very long time security. So some use cases and roadmaps. So here is a use case in Geneva. This is just when we vote, and you know in Switzerland we vote quite often. And then there is actually one location in Geneva where these paper ballots are counted manually by several people from different political parties and all that. And then they type the result into some terminals, and this information then goes to some data center. And of course, if this connection would not be encrypted at all, then, well, someone could cheat, or even someone could just announce the results before the government, and that would probably be extremely bad for the trust we have in our democracy. So here, and because it is Switzerland and Geneva, we could not only have encryption, but even quantum encryption here. This is still in use since more than 10 years. With Atos, okay, at that time it was still Siemens here in the Netherlands. This is really now installed in these large financial institutions. Okay, already also years ago. What is under construction now, under installation now, is a connection between Cambridge and a BT center here in this place. This is also done in collaboration with this quantum hub that we have in the UK. That's our local partner. The vision we have, not for very far future, is no longer to have, okay, here again you see Alice and Bob open here. But actually, what do you need? You need this quantum random number generator. I already showed you that this will be on a chip in a few years, very soon. Then you need some integrated photonic circuit. You already see some here. This is actually taken a picture from the Los Alamos laboratories. And then you need an ASIC for all the electronics and post-processing. But actually, with these 3 chips, you have the complete system. So there is no reason that quantum key distribution will also not shrink in size and obviously also in price. There's another very exciting development today in quantum communication that goes via the air, yet again, with drones or low-altitude satellites. So here it is with drones. There are quite some projects now in Europe, but also in Asia, mostly, I guess, in China again. And so the vision is really that to break this 400-kilometer barrier, you just go via a drone. So you establish a key here, the drone moves, and then has downlink further. So the drone acts like the trusted node. Okay, and maybe later you have it transatlantic. Okay. So here is 3 examples of use cases, which I find very interesting because they go beyond just QKD. It's really a complete solution that IDQ developed. So the first one, actually it's the same picture I already showed you, but in the meantime, KeyMiles was bought by ABB. But okay, we could keep the connections to these people. So this was really contributing together with the KeyMile, now ABB engineers, to develop this cryptographic card holding a quantum random number generator on it. Actually, there are even more than one for redundancy reasons. And this is really applied to critical infrastructure security. The second use case here is based on our quantum random number generator again. That is with a national bank, actually not a European one, that wanted to have some digital currency, very timely topic, and they needed secure token generation. They need to have something random again. Without randomness, there is no security. Sorry to repeat that. So they asked us to contribute, and we together developed this solution for their problem. And here, again, mostly based on quantum random number generator. That was actually with some national defense agency. They also needed a very high secure entropy source. And again, here, you don't need just a little cube that gives you this entropy. You need a complete solution. So you need a complete box, which is not shown here, which implies some nice development and a product which is not just a cube, but a solution. Okay, with that, I come to the end of this presentation. And according to this clock, we still have time for questions. Thank you very much.
Yes. Thank you, Nicolas. So, are there any questions? Yes.
Hello. Is there a way to prove that your random numbers are quantum? Like entanglement you can prove with Bell violations, but I mean, you could just be cheating and giving out zeros all the time and claim it's quantum, right?
Yeah, of course, if we'd always output a zero, probably people would notice. But no, it's a question indeed. So could it be that in this little box, you just have a memory stick, and the memory stick has actually recorded some even quantum random number generator, but the ones that are then produced from this box are known, of course, to us in this case. No, the way this present-day product works, you have to trust indeed that we did put the right thing inside. Maybe once it is a small chip enough, maybe you could go around that. The fact is that we can prove that these kind of devices produce quantum randomness if we had two of them and we violate Bell inequality. You mentioned, I think, Bell inequality, isn't it? So you demonstrate entanglement, and a good way, the most efficient way to demonstrate entanglement is to violate this Bell inequality. So this is possible, and people are doing that, but this is not yet commercial, and you see the complexity. You need two of them. They should be space-like separated, or at least you have to make sure that they don't communicate and all that. So actually what we do is not to take both of them. We sell only one of them, and the other one has to be virtually there. So the presence of the second one must be possible, and if we put the second one, then we would violate Bell inequality, and then we could guarantee the security that the outcome is truly random. But in the box, or in this little cube, you have only one of them. And so in this sense, you have to trust that we indeed have this light source and the two detectors in the cube. You're right.
Any further questions?
There is one
Yes.
at the very end.
Yeah, thank you. You are showing a lot of infrastructure that couples a quantum component like the single photon source with a lot of classical components, and I'm wondering if the classical components do not maybe risk the quantum nature, or for example, if you send a single photon through an optical fiber and the attenuation that you have is polarization dependent or something like that, or if your beam splitter, which is a classical device, in some sense doesn't have a preference.
Yeah, so if we would use polarization to encode our qubits, our quantum bits, that would indeed be a problem in most optical fibers, because optical fibers are not perfectly circular, so there is indeed some birefringence or even polarization mode dispersion. But we don't use actually polarization to encode the photons. We use something which is called time bins, so we have actually two times separated by a few nanoseconds, and the photon may be in superposition of being in the advanced and the delayed time bin. And then, the photon will not jump from one time to another time. Of course, then you have to make sure that the dispersion of the fiber is low enough, but that's easy, that you can easily control. So you have indeed to go and use the appropriate degree of freedom which are compatible with existing and installed commercial optical fibers. And the same for all the electronics. I mean, everything has to be compatible, but except, I would say, with this encoding of the quantum system, the rest is really standard electronics, standard processing. There's nothing really special.
Okay, thanks. We have time for more. Yes, over there.
I have two questions about the quantum links. The first one is, could you imagine them behaving like routers? If you have two parties communicating with each other, but you want to include the third party or build an internet of quantum, could you include routing, or do you need one connection from each participant to each other?
No, you could do this routing. Yes, you could do the routing. So indeed, I didn't really show here. Well, there was one slide where you had these kind of triangles, but you could go really to a 2- or 3-dimensional network, similar, really the same kind of architecture as you have in classical communication, and also very clearly, if one connection would be corrupted or just broken, you can then go around it. I mean, that's the same as for any networks, any communication networks. So the difference is that the distance between the nodes cannot exceed a few hundreds of kilometers, which, by the way, is also the case in continental classical optical communication.
Okay, thank you. And the second question would be, if I was an attacker and would gain control over one of these quantum links, could I actually abuse this, or am I safe? Because, as you showed, Eve can't, well, attack the quantum link, but if I intercept between the two quantum links in the connector, could I then eavesdrop?
Yes, so if the eavesdropper gets access to a link, let's say the optical fibers, there is no way for her to do any harm. Well, what she could do, of course, is just to take a scissor and cut the fiber, and then that cuts the communication. But she would not gain any information by doing that. Just cuts the connection. Now, if she gets access to one of his trusted nodes, that would be a failure. And if it is just really on one line, then she would get full information. So these nodes have to be trusted, indeed. One way to go a bit around that is to imagine in a network that you have more than one way to go from Alice to Bob. You have maybe 2 or 3 paths. And then you establish your keys along the different paths, and you take the XOR, so addition modulo 2 of all these. And then even if all links except one are under the control of an adversary, provided one link remains secure, that's good enough.
Okay, thank you.
Okay, thanks. Yes, there's another question here.
You mentioned those trusted nodes, and already one solution with the XOR to get around this danger that some of them are overtaken. Are there other solutions or other ideas to make it more secure using trusted nodes?
Well, with trusted nodes, not so far, not as far as I know. Of course, the good solution, but this is still a bit more futuristic, is these quantum repeaters. Then, with a quantum repeater, even if the adversary would hold the quantum memory and everything there, she could still not access any information, because the connection would remain really on the quantum level all the way. It's a bit similar to what we have. Okay, most of you are too young for that, but the classical communication, for a long time, we had also only a finite distance, and then we had to go from optical to electronics to amplify and regenerate the signal, and back to optics. And that was the solution until these erbium-doped fiber amplifiers were invented in the 90s. And, or maybe 80s, it started, 90s, really. And then that changed completely the picture for classical communication, because you could really remain optical all the way. That's what is used today. So here it's not a matter of remaining optical, but it's a question of remaining quantum. And with this quantum repeater, you could really remain quantum all the way, but the technology for the quantum repeater is not yet ready. So we use this trusted node. And the trusted node could be either installed in a basement of a bank or of a governmental agency, or in these drones. But of course, then the person controlling the drone has some power. If it's a government, okay, depends then on which government, and okay, so on and so on.
All right. I don't see any. Oh, yes.
There's one
There's
more
one.
My question just builds on the previous question. So these quantum repeaters, what is the time scale until when you assume that they are ready for commercial production? And what are the, second question in these quantum repeaters, what are the perturbations nowadays which limit the efficiency or this rate, which was at 20% physically?
Okay, so here I'm a bit embarrassed because I think that about 10 years ago I said in 10 years we have them, and we don't have them. So I guess it's in the future. I don't know. It also depends on how much money you put in. So there is now in Europe this big flagship project on quantum technology, and of course one of the big projects that has been submitted, they are presently under evaluation, will be on these quantum repeaters. The leading house is in Delft in the Netherlands, but okay, Geneva is contributing, okay, people, well, in Munich, in Garching are contributing, and so on and so on. Now, if you put enough money, I guess in 5 years we have it, because essentially everything is working, and even every single parameter has been achieved, but not in the same system. For instance, for the efficiency, you mentioned is 20%. So today, some people have demonstrated even, I think, 80% or something like that. I have to say that probably below 90% would not be sufficient. So you need really very high efficiency. Okay, for us in quantum optics, 90% is a high efficiency in order to really be able to beat the direct communication, and that means to overcome this 400-500 kilometer distance limit. Let's say that the goal is really to go to 1,000 kilometers. With 1,000 kilometers, we cover a big part of Europe, let's say. So at least five years, depending on funding.
Thank you.
Okay, I see one more, maybe in the back over there. I can.
Thanks. Could you circumvent something like photon loss with, say, a repetition code?
Yes, in part, indeed. If the source, instead of, in my example, it was at 10 gigahertz, if I go to 1 terahertz, of course I gain a factor 100. So it means I get not a photon, a click on my detector every few centuries, but every few years. But you see, it's not really a big progress. So indeed, I mean, there is certainly the possibility to go faster. And the other possibility also to go a bit around this blockage is to use multiplexing. Wavelength multiplexing, as is done routinely in the classical domain. We can also do that on the quantum and use maybe the 128 channels with a wavelength division multiplexing. And that would again allow us to gain a factor of 100. And then, okay, we get a bit closer to the real goal. But I guess at the end of the day, you will need to have, indeed, sources that are faster. That's probably not the most difficult. You have this wavelength multiplexing. That's certainly also feasible and not too difficult. And then you have the quantum repeater, which is the real elegant solution and the most powerful solution, but also the most difficult one.
Okay, we have 3 more minutes till the coffee break starts. So if someone else has a question, yes, over here.
So what I'm taking with me is until we have the quantum repeaters, the system with the trusted nodes is, I would say, as secure as it is right now, because I have to trust the big internet nodes to not eavesdrop my communication, and as it's currently happening by the government intelligence agencies, they just eavesdrop and store now and decrypt later the data. They will have a trusted node in their hand. So for me, I personally, I think I will wait until the quantum repeaters will be in place.
Okay. Yeah, I of course understand what you are saying. You don't need that these trusted nodes are in the hands of the NSA, of Google, or whoever. For instance, in Switzerland, you can really imagine that you have that the trusted node would be in each local government of every canton. And so when every city is really, in Switzerland especially, but it will be the same in Germany, really only a few tens of kilometers from each other. And then you would have no problem, even if there is some I don't know, a Cisco server in between two cities, the trusted node for the quantum communication would be really in the town hall of the local governments. But you would have to trust the governments. Anyway, that's when a completely different kind of discussion we could have is, do we want really cryptography with a governmental control or not? And okay, that's an endless debate and an interesting one, but a very different one. That's politics. It's no longer technology. But today, so we can offer trusted nodes under governmental control and make sure who has access to them. And in between, again, you have really the quantum security guaranteed.
Okay, thank you. So then, if there are no more questions, thank you again, Nicolas, Gisin.
Thank you.
Thank you again. And we'll have a coffee break now till 11:30.